Welcome to RCast, the official podcast to the RChain Cooperative. RChain is a complete, concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the Director of Content for RChain. Each week on RCast, I'll be talking with the founders of our portfolio companies, as well as co-op members, staff, and other figures in the RChain ecosystem about the most pressing issues in blockchain today. Please check out rchain.coop to learn more about the platform, our community, validator sale, and information on becoming a member.
We're talking this week about an approach to computation that has a long history. In the same way that the design level thinking was, the talks that we gave were kind of focused at the calculus level, going up and considering calculi themselves as abstractions. Here we're we're atomizing, we're going downward and reducing the amount of structure in the calculus in order to find some sort of finer grained or smaller building blocks in the calculus itself. These are called combinators. We've got here Mike Stay, who co-wrote this recent paper that we've been working on for a little while, and Christian Williams, who's been a regular on these RCast podcasts. Why don't you guys weigh in on how you think about the work on combinators?
Combinators were something that Schoenfinkel came up with to deal with bound variables in logic. So whenever you say for all x, p of x is true, it's some property p that holds about all of the things you're talking about. That for all with the x there introduces this variable that is bound then in what comes later. In English, you could think about modeling statements in English using predicates. Like if I say Mike likes toffee, you'd have this likes predicate, and then it would take two parameters. One is the subject, which is Mike, and the other is the object, which is toffee. And if you try and parse English that way, it works until you get a word like everything. If you say Mike likes everything, there's no single concept that fits there. What everything does is take the predicate and put this quantifier up front. For all x likes Mike x. So Schoenfinkel, in trying to get a grasp on how these bound variables would work, discovered that he could actually get rid of them. There's a wiki page on combinatory logic. You can go look at it. The universal basis for combinators that makes them just as powerful as lambda calculus is called the SKI basis. You can think of S and K and I as addressing schemes. That you have some term and you want to insert it into some other term. Right? That's what X is doing. It's a placeholder for some other thing you're putting in there. So when you say Mike likes everything, it's a placeholder for any particular thing, and we're quantifying over all of them. So the variables are marking a spot in the term, and because in lambda calculus, it's an applicative calculus. That means that you're taking these functions and applying them to data to get the result. It's one big tree of applications and lambda abstractions. When you're eliminating the lambda abstractions, all you're left with are applications. And so S and K and I are is an addressing scheme for how to get to the spot you want to be at in the application. S says X might appear to the left of the application or to the right. K says it doesn't apply here, and I says it does apply here. So S duplicates the data and sends it on down to the right-hand and left-hand side. K deletes the data, and I sticks the data in right there. Now, for linear lambda calculus, where you can only use data once, exactly once in an expression, there's a different basis. It's BCI. calculus. And B says it appears on the left, and C says it appears on the right, and I says it appears right here. Combinators can be thought of as addressing schemes for getting data to where it needs to be. Now, when you only have a single tree of applications, it's pretty easy to do. But when you have a soup of processes, then it gets more interesting. And so when you are sending messages between processes on names, the names themselves are addresses. And so the idea of getting rid of names in pi calculus is a very odd thing to do. When Yoshida was trying to do this abstraction elimination, she was able to get rid of the part that looked like lambda calculus and came up with a really nice set of combinators there, but she still depended on using names.
On the fresh generation of names.
Yeah,
right?
on the fresh generation of names. So left in the new name operation. When we tried to get rid of it, it was a little tricky. Essentially, Greg's insight with Matthias Radestock was that combinators have names. I mean, this is a retelling of the story. It's not how they thought about it originally. But the upshot is combinators have structure that tell you how to get to a particular spot in the term. And so if you're going to eliminate names, you have to have something else that has enough structure to tell you how to get to where it's going. And so they have this argument that you can't implement an infinite set of structureless atoms on a computer, which would be needed for a true model of the pi calculus. Instead, we have to represent them with internal structure on a computer. So we might as well embrace that. And then the question is, what sort of internal structure should we use? As Greg really likes to do, he separated the calculus into the pi-like part that has names and the set of names that have their internal structure. And then he said, well, I've got a set of things with internal structure that is the pi-like calculus. I'll just close the loop and take the fixed point. And they'll have this nice theory that doesn't depend on anything else for the Rho calculus. And in this case, once you do that, it allows you also to exploit the structure of the names to use them as locations of processes. And so we can get rid of the fresh name component of the calculus and just use reflection instead.
It's a nice description. It's a good summary of what the paper does. There's another aspect to it, which I learned the hard way back when I was doing a variant of Xlang inside Microsoft. We were looking at a language called Highwire, which was sort of son of Xlang and maybe a halfway point between there and Rolang. And we were quite interested in a combinator-based compilation scheme. And so we actually implemented in the same way that the OCaml people started off with a combinator-based implementation, and the Miranda people, David and Turner, implemented a combinator-based scheme for Lambda. We implemented a combinator-based scheme for this pi-like language and discovered, to our dismay, this incredibly huge exponential growth. It would just swamp our machines. Like even toy programs would just completely swamp our machines because of the exponential growth. So the interesting thing is that while it does make it easier to reason about certain aspects of programming, it really doesn't make it easier to express programs and write them down at scale. There's an enormous amount of compression that happens when you have an abstraction-like capability. That turned out to be a really interesting, hard-won insight that we got about the combinator stuff. But I was curious, Christian, as someone coming to this fresh, what's your thinking about combinator-based approach to computation?
It's a really interesting approach. That's something I was always wondering about with combinators is they give a nice variable-free description of languages providing this compilation scheme. Yeah, I always wondered if there was going to be this blow up in the size of the program when you actually tried to implement it. How do you get around that kind of issue?
Yeah, I mean, in general, I argue that lambda abstraction or abstraction in general, binding is a good thing because it gives you this really powerful abstraction mechanism, and that's why I've been a proponent of a higher level view of abstraction. I really like the nominal stuff, or the stuff that Fiore and co have developed, where you make abstraction alpha equivalence and all of that phenomena be worthy of a first-class representation in the theory.
That's the other thing that I've been wondering about, because we've been talking about that stuff a lot, and I'm hoping some of my research is going to involve it. And so far, I'm not really understanding how we might take a nice, higher level approach to describing binding, versus how does that relate to this totally opposite perspective of trying to break Rho down into these combinators.
Yeah, so I mean, one of the reasons that Mike and I have been interested in the combinator approach is because it does alleviate the ladle work from having to worry about binders. We can give a completely binder-free account of the ladle algorithm, so we can have a notion of ladle that is not equipped to handle binding phenomena, and then apply it to something like the Rho Combinator discipline, and then get a ladle like type system, or a ladle derived type system, for a calculus that we know is rich enough to encapsulate or encompass all of the mobile capability. It has that advantage, although, as we've talked about, there are some practical disadvantages because you really don't want to use that for programming. If you have any way to do abstraction at all, that's a far superior way to program in reality.
Have y'all implemented this compilation scheme yet for Yoshida's combinator?
I mean, I did it a long time ago, like back in the early 2000s, I did that. Having done that implementation, I actually did that with the guy who is currently the CEO of a company called MindTouch. Together, we wrote that compiler, and we were like just shocked at how big the thing got. Mike, I'm curious as to what your thoughts are with respect to the ladle program, and how we take it with respect to the combinator stuff versus some nominal account.
Yeah, so nominal issues are tricky. Gabay and Pitts invented this idea of nominal sets, and then Clouston turned it into nominal Levier theories, which is sort of building the mechanics of variable substitution into the language that you're using for describing your programming language. So it's a way of souping up your Levier theory. For anyone who doesn't know what a Levier theory is, it's very similar to the idea of an interface in your favorite object-oriented programming language, that you describe some data type using the language of interfaces. And then the implementations of that interface are all the mathematical gadgets of that kind. So you could have an interface for employees, or an interface for monoids, or an interface for whatever structure you have in mind. In this case, the language of nominal Levier theories lets you talk about binders for variables, reifies them. The unfortunate part is that the idea of a nominal Levier theory is very, very new, and there's not a lot of information about how well it works with the existing theory. How does these new features change what it means to be a monad? So, for example, any Levier theory corresponds to a finitary monad. What do the nominal Levier theories correspond to? Nobody knows, or at least I don't know.
Yeah, I think
so,
they mentioned that as future work in the Clouston papers.
Right. So that's a downside. There is a model by Stark for doing binding, but that's all in terms of functor categories, which you don't interpret in set. So it's a different kind of denotational semantics that's rather more complicated. Stark's approach is a more complicated notion of denotational semantics. In lambda calculus, a lambda term corresponds to a partial function. It's very clear how to interpret it. And so if we can talk about this stuff using something close to a denotational semantics that we recognize, then that'll be helpful. And
Yeah, well,
Christian's work goes a long way towards that, is laying down the basic theory involved in a graph-enriched Levier theory. This is one that lets you talk about rewrite rules between terms.
Yeah, I've really started to fall in love with enriched theories, and it just gives you such a general framework for describing any kind of formal language with accompanying operational semantics. Yeah, our paper is almost done, and we've just been having fun thinking of just a broad range of examples. But it seems like the main thing that's missing from it is a notion of binding. And so I think once the right notion of binding is put into this framework, I feel like you'll be able to do huge amounts of computer science within that and translate most programming languages into this nice mathematical framework. But like Greg was saying, recently I have been investigating an alternative approach to the nominal stuff, and that is with the Fiore's abstract syntax with variable binding. It does involve functor categories, and it takes a little more time to get used to, but it does seem really nice. And Greg and I think, arrived at the conclusion that reflection, just like the reflective capacity of the Rho calculus, allows for us to bypass a lot of the machinery that nominal set theory involved, because a lot of the machinery was just about shuffling around the atoms of the names in the pi calculus, for example. But because with reflection, you can dynamically create new names in a systematic way, hopefully a lot of that won't be necessary. We won't have to worry as much about names, and we only have to worry about variables.
Well, one of the things I think is so important is that I'm not sure that people in the wider programming community or in the wider audience for RChain understand like how subtle a lot of these things are, right? You know, the notion of binding, like we've got 3 different possible explanations on the table, right? So we've got the combinatory explanation, we've got the nominal work of Cabai and Pitts, and then we've got the abstract syntax of Fiore et al. And each one of them is compelling in its own right, and it has its own agenda and it's not always the case that those agendas are lined up exactly with, you know, how programming is used in industry, or
yeah, and that's not even mentioning the one where you build in the machinery for name handling into the theory itself, right? We could write a term constructor for building environments, and then handle all of the substitution and lookup and so on in the theory, as opposed to
that's the explicit substitution.
Yes.
So that's yet another one. But the important point is that each of these different features of programming languages, whether you're talking about binding or fresh name generation, and those are separate, they're different ideas, as Yoshida shows with her work, or you're talking about concurrency, or you're talking about monadic abstraction, any of these language features is relatively subtle. On the one hand, a good accounting for them, there's a certain amount of work that's involved. But on the other hand, if you want to get type systems that allow you to constrain and control and see into the operations and structure and mechanics of your programs, then you also have to have this stuff nailed down fairly well. And that's why, you know, sometimes it takes a while to really elucidate each of these features and how they interact. And that's been for me, you know, a part of both the joy and the frustration of the journey. one of the things that Mike has reiterated several times is that giving an account of names is tricky. We submitted an earlier version of this paper to a conference called Express SOS, and the reviewers were quite kind, in the sense that they said, it's written with a consistently high quality. They encouraged us. They said this is an important line of research. They said, don't give up on it, but we have to reject it because there's a type error in one of your equations. And so I was like, what? And I went back and looked at it, and I realized, they're right. There's an easy fix. But then when you do that easy fix, it kind of ripples through more than half a dozen equations throughout the paper. And so it was a lot of fine, detailed work to make sure that I threaded the correct type information through all the equations. So it's very tricky. It's not a slam dunk. You have to. It's a pretty subtle phenomenon, and I think people should appreciate that about a lot of programming language semantics. We don't really know what our programs do.
I just love thinking about the problem of binding and substitution, because it's like the simplest possible aspect of computation that everybody takes for granted, but it's really kind of the most fundamental.
Yes, I agree 100%. And it's been a problem that's been on people's minds for a long time. I know that John Reynolds proposed that for fresh allocation, he proposed the functor category solution. My goodness, it's probably 30 years ago now. Then the Schoenfinkel proposed the combinator stuff. Is that 60, 70 years ago, Mike?
Easily. I think it was the 20s.
Yeah,
Oh, wow.
yeah,
I was thinking 30s, but
90
wow. Okay, wow. That's a really long time. I think that the takeaway is that people should have from this is that these are really basic aspects of programming, and it's taken the better part of a century to get a handle on how these things actually work. There's a lot of depth to what programmers do. We kind of sling these concepts around, but in many ways it's the miracle of being able to use your hand, right? Like nobody picks up a coffee mug by thinking, okay, well, in order to do that, I have to use the tendons in my thumb and leading to my thumb and my the top two fingers, and I have to use the tendons down the forearm, and nobody goes through that kind of low level instruction with respect to the mechanics of the operation of their arm. They just do it. Same is true with like driving a car, right? People drive cars without having a clue as to how the engine is actually operating. And in the case of like the Toyota Prius, like the engine is even sealed over now. You can't even do your own maintenance on the car. There are these kind of phenomena where we use them, but we don't know how they actually work. And that's what's going on with a lot of programming languages. But unfortunately, that leads to a lot of cost in the industry, right? So with JavaScript, there's a clear example where we've got this language that a lot of developers use to put together the infrastructure of the web, and yet we don't really know the semantics of JavaScript. Not only do we not know the semantics, not knowing the semantics makes it hard to give a really compelling type system.
Semantics differ between implementations. There is a formal semantics that has been implemented, but it is horribly complicated.
Exactly.
I mean, it's a several hundred-page document.
Right, but I guess my argument is that the average web slinger doesn't know that document, doesn't understand the implications of
absolutely, yeah,
that document, right? So they're kind of slinging code without really understanding the meaning of that code.
They're restricting themselves to a semantic subset of JavaScript.
Using idiom
called,
convention.
I think, Lambda.js.
Yes, that's right.
That has identified that semantic subset and given a much easier formal semantics as long as you restrict yourself to that case. But you have to be sure that you're setting up your environment yourself. You can't trust that anybody else hasn't broken those semantics when you go to program if somebody else's code runs before yours.
Oh yeah, yeah, exactly. And then there are languages like Ruby where you can monkey patch. You can slide in underneath the definitions of operators and change the meanings of other people's programs.
You can do that in JavaScript too, not with combinators, but yeah, most of the basic functionality.
Oh yeah, yeah, that's right. That's right. I'd forgotten that monkey patching was available in JavaScript as well. These are pretty subtle issues, and they end up resulting in a very high cost of development because one can sling code, not really know what it does, and then be very surprised at a lot of different outcomes. And what we would love to do is to be able to constrain those surprises at least a little bit, right? And that's where the value of good type systems come into play. In order to have the type systems have the most visibility into these languages, we need to have a good account of all the features and how the features interact. And that's really at the heart of the work that the Rho Combinator stuff is doing, and what Christian is doing with the enriched Levere theories, is to explore and consider each different way we might think about these features, and so that we can then give good type theoretic accounts of them, so that we can climb, he'll climb up to realistic languages and give them good solid type systems, but do that in a way that's algorithmic, right? Most type systems to date have been handcrafted, right? So when you talk about Scala's type system, that was handcrafted. And the first version of that was handcrafted in a way that wasn't even sound, right? So, which also results in a kind of cost to the industry. So if we have an algorithmic approach to the generation of these type systems, then we get soundness and completeness of the type system as a by the construction of the algorithm. And so all of this fits together, marching towards a program, a research program that delivers type systems across a wide range of computational phenomena. The Rho Combinator paper is just carving off one tiny little slice of the language features to do that. Any other thoughts, you guys, about this work or how it applies to blockchain or anything else?
Yeah, I'm just curious to hear y'all talk more about this paper. I'm still working through it myself.
Well, sure. I mean, I can say a few words, and I'd love to hear Mike's perspective as well. But one thing is that when we reworked the paper, I took a little bit more time to explain the role of compositionality in the paper, and sort of talked about it at two levels. One level is that once you start thinking compositionally, it's actually a surprise that the community didn't find the Rho calculus much sooner. If you write it down diagrammatically, the idea of putting a loop in is just like, well, I mean, this is like standard feedback loops in circuit design. So it should have been found right away. People really haven't gotten the compositional thinking into their bones yet, despite the fact that the community, the computer science community, the category theory community, the types community, each of those communities is really committed and understands the power of compositionality, but it still takes a long time to internalize that style of thinking. I wanted to point that out. And then the other level of the role of compositionality that I point out is that effectively the proof of the correctness of the approach comes by composing the correctness that we get from Yoshida. Because, essentially all we're doing is we're taking her technique and we're threading the reflective machinery through her technique. And that's it. That's the essence of the paper. So in some sense, it's not a particularly surprising result. We're adding a couple of combinators to her combinator set for reflection, and then the deref, which takes the reflective thing and turns it back into a running program. And then just making sure that wherever she uses new, that we replace that with an appropriate appeal to the reflective machinery. And the biggest insight that one needs in order to do that is just that with the reflective capability as it is described for this family of calculi, you can't ever have a process the quote of which is used in any of the names of that process. So if P uses X, X cannot refer to or be built out of the quote of P. And so automatically, any name that's built from the quote of P is fresh or distinct from any of the names used by P. You can locally find something that's fresh just given a process. You don't have to go and do anything magical to go to a name service and say, hey, give me a fresh name, or go to some infinite supply of atoms and say, hey, give me a fresh name. You get this kind of local property of freshness that is a nice feature of the reflective machinery. Those are the key insights as I see them in the paper. But maybe Mike has a different take on this.
That was it. It was basically taking what you had done to replace nu and replication in the pi calculus and then porting it over wholesale to Yoshida's combinator setup. And so the paper itself is very technical, has lots of things going on, translating from pi calculus to Rho-Lang, more or less, Rho calculus, and then translating from Rho calculus to Yoshida's calculus with her machinery copied in there, but then taking the complicated machinery from the translation of pi calculus to Rho-Lang and embedding all of that complication into the translation into Yoshida's. It's a bunch of code, but the ideas are very simple.
Exactly right. That's the nature of that paper for sure. Does that help you, Christian, in terms of reading the paper? Is like knowing that that's what's going on?
Yeah, I was wondering what was Yoshida's original motivation for the combinator?
I would encourage anyone who has the interest and motivation to go and read the paper, because with the combinatorial approach, she's able to get a handle on expressiveness that is a very subtle phenomena in computation, right? I mean, the stratification of expressiveness that gives rise to the hardest problems in computer science. P equals NP is an example of, an expressiveness stratification problem, right? And that's still an open problem after, decades and decades. So what Yoshida does is after she proves that this combinator set forms a basis for expressing all pi calculus programs, then she looks at subsets. And she says, well, if I don't have this combinator, what can I express? If I don't have that combinator, what can I express? And she gives a lovely little diagram which shows the expressiveness categories built from the subsets of the combinators.
The same sort of thing happened in lambda calculus, and we got linear lambda calculus and affine lambda calculus. She was breaking it down in much the same way. Given different subsets of these calculi, what sorts of programs can we write? What logics do they correspond to?
Yeah, exactly.
I don't think she actually got into which logics they correspond to.
She certainly was able to classify the class of programs. That's what her diagram. If you factor that through some ladle-like construction, then you'll get these a similar kind of thing for various logics.
Would RChain have use for that kind of stratification?
Yes.
I mean, with Rho-Lang?
Yeah.
Yes, in the following sense. My sense is that financial contracts are restricted in a way than just general application programming. Right? So if you want to write a game, you probably want the full range of Turing complete. But my guess is that nearly all financial contracts need to have a notion of reversibility. You can do a notion of reversibility in the Rho calculus by doing a continuation saturated form, and then since every step in your computation then gives you a reification of the continuation, you can squirrel away your state before you take any step. That's a really onerous and heavy-handed way of doing things. The other approach would be to restrict the expressiveness of your contracts so that you get reversibility without the same kind of cost, without the same kind of overhead. And that, I think, would be of really great use for reasoning about financial contracts. I mean, effectively, the financial contracts, I would submit that they're going to be covered by some linear programming discipline. because you basically want everything to balance out, right? And so if it's a linear programming discipline without the use of bang or whimper, some kind of replication operator or storage operator, you get reversibility for free. That was an interesting point that Samson proved almost 15 years ago now. So I think that would have significant applications for restricting and type checking that, oh, this contract is within the expressive domain of financial contracts.
So it looks like Yoshida's combinators are non-linear because they have the duplication and the kill. So is there a corresponding linear replacement of those?
Yeah, it's the idea exactly. Is you come up with good linear replacements. You can take inspiration from BCI. You can also take inspiration from Yoshida and Honda and Berger did a lot of work on linear type disciplines for constraining pi calculus programs. So they were able to use this to give a type guided interpretation of the lambda calculus into pi. But you can use it also just to pick out linear subsets, right? And so you can go the other way around. So you use a linear type discipline to pick out a sub language and then compile that down into the combinators. You'll identify the restricted set that way. So you can kind of go either way around, right? You come up with your own linear combinators, or you can come up with a restricted usage of the Yoshida combinators. And then you can kind of compare the two results. In some real sense, that ought to commute in some way, but I don't know how to make that crisp yet.
Yeah, it seems like a big space to explore. It's definitely not one compilation scheme. I mean, these combinators are basically just like generators for the whole space of programs. And it's like there's tons of ways of presenting the Rho calculus in terms of like these generating basic programs, and each one is going to have its own ups and downs.
Yeah, absolutely. The resulting algebra for SKI starts to look a lot more like classical algebra because you don't have these sort of fancy, complicated generators like, lambda abstraction. You just have 3 letters and all the words you can form over those letters. And so it has more like a generators and relations presentation. Now, of course, there's the operational semantics, but it's a lot more like a classical presentation of an algebra. And in fact, some of the presentations, call that thing an applicative algebra. And then the same is true when you go, like Yoshida's combinators don't have that property because she's still got new everywhere, right? It's sprinkled all throughout. But when you go through the Rho Combinator thing, you recover that. Now the resulting structure looks just like a classical algebra in the sense that you now just have these things that you combine with a par. So you've got some commutative operation that you can use to join up these basis elements. And so it now has a presentation that looks a hell of a lot more like a classical algebraic structure. In that sense, that's what I meant before at the top of the talk when I was saying it kind of atomizes or it eliminates internal structure of the calculus. That's what I'm talking about. You're stripping away all these fancy term constructors. You just have par. Any other final comments we want to make? We're coming up to the top of the hour.
For any listeners interested in combinators, I recommend the book To Mock a Mockingbird.
Oh, yes.
By Raymond Smulyan. It's a very cool book that teaches you about combinatory logic through this elaborate metaphor with a forest of songbirds.
Yeah, that's a really, really fun book. It's a good one. Absolutely. Next time, we'll be talking about the brain candy I sort of gave in a closed door session where I talked a little bit about some rewriting the validator harness in terms of metabolically controlled continuation and what that does. There's actually a whole bunch of results along those lines that connect up the work of the Casper work to some biological metaphors. So I'm looking forward to having that chat as well.